Hello everyone, my project for computational photography is evaluating the effectiveness of polarization-based instant image dehazing, which is based on a paper by Evolve Schechner called Instant Dehazing of Images Using Polarization. This is a physical model they used to derive their methodology. The important insight here is that the luminance at each pixel in the image, it has two components. One is the object radiance R, that is reflected off of the objects in the scene, and it is attenuated by the distance z because it's scattered by the particles in the air on its way to the camera. The second component is air light, which is the ambient light that's scattered off of the particles in the air that happens to be in the direction of the camera. The paper also makes three very important assumptions. One, air light is partially polarized, and two, scene radiance is not polarized. Lastly, there exists a region in the image where there's only air light, and this is usually the sky. Their proposed method is that we first synthesize the best and the worst polarized images from the arbitrary number of polarized images provided as input. So the best polarized images means that the polarizer is rotated in a way such that it lets the most amount of light through that's perpendicular to the direction of polarization of the air light, which means that we'll get the least amount of contribution from air light and the most amount of contribution from scene radiance, making all the objects in the scene clearer. The worst polarized image is the opposite. Next, we calculate the degree of polarization and the air light at infinity. Both of those are constants, and we calculate it by taking a patch of the image where we know all the pixels in this patch only contains contribution from the air light, not the scene radiance. This is usually the sky, and the degree of polarization means how much the image varies across different polarization angles. And the air light infinity is the strength of air light at infinite distance. Next, we can calculate the air light at each pixel. And lastly, we can remove the air light from the image, which is a matter of subtraction, while accounting for the distance, because both air light and scene radiance is attenuated by the distance z. So here are the results. These three are the inputs to our algorithm, and these are images with polarizer rotated at 0 degrees, 45 degrees, and 90 degrees, respectively. And these are the best and worst polarized images we synthesized using the algorithm. And zooming in a little bit here, we can see on the left we have the best polarized image, where the building and the red car in the background can be clearly seen. And on the right, we have the worst polarized image, where those cannot be seen at all. And this is the air light image we calculated that shows us how much air light is in each pixel of the image. And lastly, we can remove the air light from the image to get this dehazed image, where we can see all the haze have been removed and the objects in the distant background can be seen. And we also get a range map. You can see here that the little bit of car that got into the image is black, and the road gets brighter as it goes into the distance, which means this is a plausible depth map of the scene. However, there are also a few failure cases where the algorithm could not successfully dehaze the image. The first cause of failure is insufficient polarization in air light. Recall that one of the critical assumptions we make is that the air light is partially polarized while the scene is not. However, this is clearly not true in this image. On the right, I show the difference map of the three input images at different polarization angles. And you can see that those input images do not differ at all at where the sky is, which means the sky is not polarized at all. Next, the algorithm also fails when the scene radiance is polarized. Recall that we assume the scene radiance is not polarized. Lastly, we mentioned that we assume there is a patch of sky that represents the air light at infinite distance. However, in this case, I selected two different parts of the sky as the sky patch. In the result above, I selected the patch of sky that's to the right of the tree in the middle of the image. And at the one on the bottom, I selected the patch of sky that's to the left of the tree in the image. And you can see, even though they are supposed to be a uniform part of the dehazed outcome, looked different depending on which part of sky you chose.